I now call to order the Society's 2,451st meeting in the 150th year since its founding on March 13, 1871. Good evening, everyone. My name is Larry Milstein. I am the president of PSW, one of the oldest scientific societies of Washington, D.C., committed to providing a forum to further scientific understanding and inquiry. Welcome to our members, guests, and friends to tonight's lecture by Sean Andrews. I'm delighted that today's meeting is being held in person at the Cosmos Club, including a pre-lecture reception and dinner with our speaker. We plan to meet in person regularly going forward. However, due to the travel limitations of the next speaker, who will be on telescope duty next month in Hawaii, the next lecture will be via Zoom. And we will use Zoom when advantageous in the future as well. All in-person meetings will adhere to the COVID-related rules of the District of Columbia and the Cosmos Club. Proof of vaccination, including a picture ID, will be required for in-person attendance. Masking is strongly suggested, and we also suggest getting tested for COVID infection within 48 hours of the event. These requirements, of course, are subject to change with changes in the COVID-related rules of the District of Columbia and the Cosmos Club. Please check the PSW website often for up-to-date information. Of course, we will continue to live stream all meetings to YouTube for our remote audience to enjoy and to ask questions in the YouTube chat box. And final versions of the live stream recordings will be posted to the PSW YouTube and PSW Vimeo channels, where they will be permanently available for everyone to view without charge. The Society is grateful to the sponsors of the 2021-2022 lecture series for their support. The Policy Studies Organization, in cooperation with the American Public University, and a generous donor who's asked to remain unnamed. And we're also grateful to the sponsor of tonight's lecture, our very own PSW member, Erica Kane. Thank you, Erica. I am pleased to announce that the following new members have been elected to the Society. John Chernyavsky, a computer scientist, retired from NSF, interested in computer science, mathematics, especially statistics, and the history of mathematics, who learned a PSW from a PSW member. Maria Zemenkova, a computer scientist, also retired from NSF, with a wide range of interests in science, who learned a PSW from PSW member Frederica de Rema. You don't see Frederica in the audience tonight. And Sean Adams, tonight's speaker, whose interests will be clear to you in some small part from tonight's proceedings. We welcome them to membership. If you're not a member and would like to join PSW or support the Society, you can do so through the PSW Science website using the blue Join button on the upper right-hand corner of the home page. We welcome new members and we appreciate donations. Recording Secretary James Nealon will now read the minutes of the 2,450th meeting and the lecture by Francisco Cordova on the Arecibo Observatory, past, present, and prospects for the future. James, the stage is yours.
Good evening, everyone. On December 3rd, 2021, from the Powell Auditorium at the Cosmos Club in Washington, D.C., President Larry Milstein called the 2,450th meeting of the Society to order at 8:02 p.m. He welcomed new members, and the recording secretary read the minutes of the previous meeting. President Milstein then introduced the speaker for the evening, Francisco Cordova, director of the Arecibo Observatory. His lecture was titled, The Arecibo Observatory, Legacy and Ideas for the Future. The observatory is a multidisciplinary research facility conducting research into radio astronomy, space and atmospheric sciences, and planetary sciences. Built in 1963, the 118-acre facility hosted the largest fully operational single-dish radio telescope in the world, upgraded 3 times over the course of its life. Its original intent was to study Earth's ionosphere. At the time of its collapse in 2020, the 900-ton telescope platform was suspended above a 305-meter dish by 3 main towers. Its primary capabilities were its premier radio frequency instrumentation, optical and near-infrared instrumentation, lidars, and myriad other systems. Among the observatory's historic accomplishments were discovering the first pulsar in a binary system, which won the Nobel Prize in 1993, discovering the first planets outside the solar system, and detecting the first repeating fast radio burst. It was also the only planetary radar with enough power to determine asteroid orbit, with enough warning time to act before a collision. On August 10, 2020, one of the auxiliary cables that supported the observatory's steel platform unexpectedly failed, causing a 100-foot-long gash in the telescope's reflector dish. The failed cable was among the newest cables installed in 1990. A repair team was immediately assembled. They developed a safety and response plan, forensics analysis and monitoring, and repair ideas. At no point did observatory personnel suspect degradation of any of the telescope's main cables until November 6, 2020, when one of the main cables failed on the same tower. The failure exposed additional degradation of the main structural elements. Drones began inspecting the cables 3 to 4 times per day until December 1, 2020, when another main cable failed, leading to the collapse of the entire platform structure. Cordova showed drone video footage capturing the dramatic collapse. The damage assessment was total loss of the telescope platform, 35% of the primary reflector, and significant damage to the observatory's buildings. Capabilities not impacted included lidars, imagers, the ionospheric heating transmitter, and ISR transmitter elements. Since the collapse, the observatory has completed necessary demolitions, debris removal, and environmental remediation activities. A forensics analysis of the collapse by Thornton Tomasetti is still underway. Initial analysis indicates the preliminary cause was creep failure due to potential overload of the structure. In other words, a latent problem in the telescope's original design. The observatory is now working towards historic preservation and planning for the future. The science instruments that were not impacted by the collapse have continued to operate. The observatory has accordingly shifted its ongoing research to rely on those operational instruments. The speaker said the collapse prevents an opportunity to develop a new anchor instrument at the observatory that exceeds the capabilities of the original 305-meter telescope. He then presented multiple concepts. The next generation Arecibo telescope, or NGAT concept, is a compact phased array, trying to give the sensitivity of a single dish with the flexibility of simultaneously observing multiple areas of the sky. The NGAT would have 5 megawatts of continuous power, transmitting at 2 to 6 gigahertz, 0 to 45 degree sky coverage, and 10 megawatt peak transmitting power at 430 megahertz. If constructed, the NGAT would lead global planetary defense against errant asteroids, leverage its power to fully map the ionosphere, and pioneer new frontiers in radio astronomy. The team explored different telescope configurations that would meet the requirements that optimized scientific output, including single dish, typical array, a hybrid, and an array of dishes on a plate-like structure. The most recent design proposal is a compact phased array of 1,112 9-meter reflectors equipped with cancellation technology to protect radio frequencies, increasing sky coverage 250% over the collapsed telescope. The speaker said the biggest concern was whether such a large structure could be feasibly built. An alternate concept is to split the compact phased array into 7 panels to reduce engineering complications while minimizing shadowing. This concept would allow the NGAT to be constructed and begin operating in phases. At 3 panels, the split array would already be more capable than the collapsed telescope. The observatory is now working to gather support for the estimated $500 million project and hopes the NGAT construction can begin as early as 2025. The speaker then answered questions from the online viewing audience and those present in the auditorium. After the question and answer period, President Milstein thanked the speaker, made the usual housekeeping announcements, and invited guests to join the society. President Milstein adjourned the meeting at 9:42 p.m. The temperature in Washington, D.C., 9 degrees Celsius. The weather, partly cloudy. The number attending live on the PSW Science YouTube stream, and here in the auditorium, 68. Cumulative views on the PSW Science YouTube and Vimeo channels, 279. Respectfully submitted, James Heelan, Recording Secretary.
Thank you, James. Are there any questions or comments on the minutes? Online listeners, if you have any questions or comments, please enter them in the YouTube chat box. Otherwise, send comments to Corresponding Secretary Robin Taylor at correspondingsec@pswscience.org. Hearing no objections, I will entertain a motion by a member to accept the minutes as read. And do I have a second? All members in favor? Aye. All members opposed? Hearing no members opposed and all members present apparently in favor, the minutes are accepted as read and will be posted to the website in due course. We now turn to tonight's lecture on planet formation and the structure of protoplanetary disks. It's my pleasure to introduce tonight's speaker, Sean Andrews. Sean is an astrophysicist at the Smithsonian Astrophysical Observatory of the Harvard Smithsonian Center for Astrophysics. He also serves as the director of the SAO Radio Telescope Data Center, and he's a lecturer in astronomy at Harvard University. Sean's research focuses on the formation of stars and their planetary systems based on astronomical measurements with radio telescopes, particularly long baseline interferometers operating at wavelengths around 1 millimeter. His research has led to a broad range of discoveries about the reservoirs of planet-forming material around young stars. Among other notable particulars, Sean was principal investigator of the disk substructures at High Angular Resolution project that established the power of high-resolution millimeter wavelength imaging to probe key physical processes associated with planet formation. He is an author on more than 220 scientific articles. Among other honors and awards, he's received 2 Secretary's Research Prizes from the Smithsonian, has been a Tinsley Distinguished Visiting Scholar at the University of Texas, Austin, and was awarded the Hart Tenledy Prize and the NASA Hubble Fellowship. Sean earned BS degrees in physics and mathematics at Northwestern University and an MS and PhD in astronomy at the University of Hawaii's Institute of Astronomy. All questions will be fielded after the lecture during the Q&A session. Sean, the stage is yours.
Thank you, Larry. Thank you very much, Larry. And thanks so much for having me here. I'm really excited to tell you about what we've been working on in the field of planet formation. I should say, I think about this as more observational planet formation, which is a field that didn't exist when I started astronomy. Really, it was a very theoretical field on the astronomy side and a very real, tangible field on the planetary science side, focused on the formation of the planets in our solar system. I like to start actually just showing this beautiful piece of art from Alma Thomas. It was very fitting, a DC artist from the 1960s. And you'll sort of get why I like this, this piece of art, particularly when you see some of the images I'm going to show you. So let me just set the stage. This is what one slice of the multi-dimensional data set that we have on planets, right? Here I'm plotting what was known, 4,576 planets in the NASA Exoplanet Archive that were confirmed measurements of exoplanets and planets in our solar system, which are marked with these gray diamonds, that were in the archive last week when I made this plot. It's now 4,800 something. It's very difficult to keep track of. I try and update it once a year. Just marked in different colors by how they were actually measured for the first time. But just to give you an idea here, this is the mass on the y-axis of these planets relative to Jupiter, right? And on the x-axis, you see the orbital semi-major axis, how far they are from their stars. And what you notice here, probably just looking at it, is there's immense diversity in the planet population that is not reflected in our own solar system, right? Again, the solar system planets are in the inner part low mass and the outer part higher mass. But you don't see a lot of planets out here. And you might think, actually, wow, our solar system's actually odd. But we don't actually know that yet, because a lot of the white space, especially over here, is just limitations in the measurements. Right? We don't actually have access to planets at those large distances. For example, if we use the Doppler method, which is measuring the reflex motion of the planet, or of the star in response to the planet's orbit, to actually measure an exoplanet at an orbit of, say, 100 AU around a solar-type star, the period of that planet is 1,000 years. Right? We don't have 1,000 years of such measurements, so we don't have access to those planets yet. But what we do know, just looking at where we actually do see planets, are that there are a lot of planets in other planetary systems that are not like, we don't have those such planets in our solar system, right? We don't have Jupiter mass planets at 1 astronomical unit, the distance from the Earth to the Sun. If we did, we would not be here. Right, so this just gives you an idea of the immense diversity of the planet formation process. The outcomes can be quite different than what we see in our own solar system. I would say it's still an open question, at least in my mind, of whether or not the solar system is an outlier or not. I don't think we have the information for that yet. But certainly there's a lot of other examples of different kinds of planetary systems, right? So that diversity in the planet population in this axis of parameter space and also many others is primarily a manifestation of the formation process of those planets, right? Typically what happens, at least let's focus on the higher mass planets, and here where we see most of the planets because they're easier to detect. Those planets don't form there, usually, right? There's not enough mass in their formation reservoir at that location to form there. What happens is that they form further out, and they follow a track like this. This is from a suite of models that do it. It's just an example. But say you form a Jupiter mass planet at 10 astronomical units. Currently Jupiter in our solar system's at 5. Something like Saturn is at 10. You form that at an early time, and it grows and accretes mass, and then it will actually migrate. Planets, the system of planet formation is just not static, right? So where planets end up, their atmospheric compositions, their masses, the orbital architectures of planetary systems are all dictated by interactions with their birth reservoir, the protoplanetary disk, right? And so when I say protoplanetary disk, I'm not saying anything tricky. You should literally think of a disk. It looks more like a red blood cell or something like that. It has a little bit of flaring. But that's what we're talking about, a rotationally flattened structure that orbits a young star, right? So obviously I wouldn't be here talking to you about this if we didn't know that those exist. But you could actually figure out that those exist without ever actually seeing them, just by looking at planetary systems, right? So if we take a look at these 4 planets, at sort of 10 Jupiter mass type planets, they're all from one system, orbiting at tens of astronomical units. Very different than what we have in our planetary system. But you can actually, because of this dark color, purple, they're directly imaged planets, small subset of things that we directly imaged, and you can see they're all sort of clustered at, say, 5 or 10 or 20 Jupiter masses. That is a pure sensitivity limit. You can only see planets right now with the instruments that we have today, maybe down to 2 Jupiter masses or thereabouts, right? Let's take a look at those 4 planets in this planetary system. This is an image from Jason Wang and Christian Marois using the Gemini telescope. At least initially, the Gemini telescope was a Discovery telescope at Mauna Kea. And you can see 4 planets in this image, and the star is sort of masked out by a coronagraph. And if you can't see 4 planets just looking at the image, you sure can see them when they move, right? When I saw this movie, which is a movie sort of for public consumption and for people like me to use in their talks. When I first saw this movie, it really sort of struck home to me that what you're seeing is a group of worlds around another star, right? Orbiting the star in Keplerian motion. And by Keplerian motion, I mean following Kepler's third law, where the planet that's most distant, this one, is orbiting slower than the others. But the important thing is that they're all orbiting in a plane around the star. They share their plane, their orbital plane. And the reason they share their orbital plane is because they formed in a flattened, rotating disk. So you can just learn that from looking at planets themselves. Of course, this is not a discovery that relies on exoplanets. This is something that people have known for hundreds of years on Earth, because you can see the planets in our solar system in a plane, right? As of this image of a planetary conjunction from 2016. I don't know if any of you remember, there was a great planetary conjunction that you could see in the night sky. So just give you an idea what you're looking at. You're seeing Jupiter, Mars, and Venus, in this case, along the ecliptic plane, which is the orbital plane of the planets, which was the orientation of the protoplanetary disk that formed our solar system. Don't be fooled, that's a star. Right? So people have actually hypothesized that planets were formed out of a flattened rotating disk structure for quite a long time. And in the 1990s, when the Hubble Space Telescope was launched, they took some of the first, really spectacular images were taken in the Orion Nebula Cluster, right? And this is one of my favorites, sort of the classical photo, where you really saw the protoplanetary disk around another system, right? So what you're looking at here, this little red thing in the center is a star, and then the black disk-like object is the disk that you're seeing actually in silhouette that's illuminated from the back by the bright sort of greenish nebulosity. Right? There had been long hypothesized from at least the 1950s or 60s that there was evidence, indirect evidence for protoplanetary disks. And if you interview my more senior colleagues at the time in the late 1980s and early 1990s, there was still a bit of a debate, and that's because particularly observational astronomers are extremely conservative and don't like to admit that the flashy thing that gets grant money is really happening until you can see it. And this was one of the few images that really brought it home to everyone. It's sort of undeniable that you have these rotating, flattened structures that are sort of on the scale of 100 astronomical units, typical size of the solar system. So I want to try and, I won't do great justice to it, but I want to try and lay out the theoretical picture of planet formation in the context of the evolution of planetary systems, and give you some idea what the traditional sort of classical planet formation model is, and how that's being revised now that we have an observational branch, observational astronomy branch to the field. So I shouldn't do this in the context of astrophysics, but I gave a rough timeline here to just give you an idea. Ages of things in astronomy are often very difficult to pin down. So note that this is a logarithmic timeline, and that means I have a lot of leeway, even for an astronomer, to give you an idea what's going on here. The important point that I want to make is that all the exoplanets we know are over here. They're sort of 100 million to 1 billion years old, maybe even older than 1 billion years old, right? They have settled into their physical properties and dynamical state after a lot of action at early times, right? And so again, I initially wanted to draw this up as a linear plot, but then you can't see anything, because basically everything happens within the first 10 million years. And 10 million years is basically the lifetime, typical lifetime of protoplanetary disk. So basically, what's going to happen is that the star itself is going to form, right? So how does that work? You start with a cold, dense molecular cloud. It's basically enormous scales of gas and dust that are sort of the skeletal structure of the galaxy, right? Inside these clouds, you might have what's called a core or an overdense region. Typically, it's in a very slight amount of rotation. Something will precipitate the collapse of that, the gravitational collapse of that core. It might be turbulence, it might be interactions with its environment, it could be compression from a supernova shock wave. It doesn't really matter for the context of this discussion, but the core will gravitationally collapse. And to conserve, or primarily conserve, angular momentum as it collapses, that small amount of rotation ends up increasing as you get down to the denser and denser scales. And what happens is material doesn't fall directly from this cloud core onto a central object, the star. It ends up falling into a flattened rotating structure on small scale, a disk. Material from the collapse is channeled through the disk onto the star to build up the mass of the star. So the disk itself is formed as a conduit to be able to make the star, right? The star formation process, I'd say is typically over by a few 100,000 years. It's sort of arbitrary what you decide is time zero, but it takes a few 100,000 years to actually make a star in its protoplanetary disk. And basically, as soon as you have a disk, you could start the processes involved in planet formation, which I'll get to in a moment. But the key thing is just observationally, we can see that disks disperse on time scales of about 10 million years, right? That material is either being eaten by the star, accreted onto the star, it's being blown away in winds into the neighboring environment, or it's being locked up into planets. Right. And the reason that we know this is happening is basically you can look for tracers of the disk material, infrared emission, for example, from hot dust orbiting the star, and that infrared emission, you look in a cluster of stars of some age, and you take the fraction of those stars that have evidence for that dust. And then you do that in clusters of different ages, and you see basically by the time you get to 10 million years, you see very low fraction of stars that still have disks. Right? So all the actions happening in this part. So the benchmark time scale that we're looking at is 1 million years, which I realize, if you're not thinking about astrophysics all the time, seems like an absurdly long time scale. But for astrophysics, 1 million years is nothing. We don't worry about things at 1 million years when the universe is 13 billion years old. So let's focus on that planet formation timescale, and let me give you the sort of classical picture of the formation of planets. This is called the core accretion model. And basically, it sort of has a natural progression. It seems a little crude when you think about it, but it's actually, a remarkably straightforward process in principle, but it's actually difficult to do. The starting point for the core accretion model is that you have a disk of molecular gas, cool molecular gas, primarily molecular hydrogen, right? And it's smooth. Now, this is the assumption that's made in most of these models. And by smooth, what do I mean? This is This is a plot, just a model of the pressure distribution of the gas in the disk, right? By smooth, I mean it just has a monotonic variation in the pressure. In disks, actually, the densities are higher, closer to the star. This is just a manifestation of where the gravity is in the situation. And the temperatures are higher because the heating of the disk material comes from radiation from the star. So the closer you are to the star, the higher temperature you have. Pressure is just density times temperature for an astronomer. And both those things decrease as you get further from the star, right? So in this case, you have a smooth, monotonic decrease in pressure and gas pressure. That's the underlying assumption number one. And the second assumption is that smooth gas disk is seeded with what we call planetesimals, right? So planetesimals would be objects that are sort of 100, people will argue 1 to 100 kilometer scale. They're big rocks like asteroids, Kuiper belt objects, right? And they're distributed throughout this smooth gas disk, maybe with some constant ratio in mass, maybe 1% of the mass of the gas, right? And then basically what happens in the classical model, that's planetesimal accretion, is that those rocks receive little nudges from the gas, and they develop relative velocities to one another, and they collide, and they grow, right? Basically, they grow slowly by accretion. Right? At some point, you build up enough mass in an individual body that we'll call a core or an embryo, that body it has enough mass that it can start to grab its own atmosphere from the gas disk, right? And then basically you can end up, sorry, I'm missing my cursor. Then basically you can end up in different scenarios depending on where you're located in the disk and how long you have by the time you get to that mass to grab an atmosphere before the gas disk dissipates. If you don't have a lot of time, you won't grab a lot of mass, and then you'll maybe be like this scenario here, where you'd be what we call, an ice giant like Neptune or something, or maybe a super Earth in the exoplanet catalog, something that's sort of like 10 times the mass of the Earth. Or if you're in the right part of the disk and you have a lot of time left to grab gas, it doesn't take actually that much time. If you get a massive enough core, you can get a lot of mass in a hydrodynamic collapse onto the core, right? So you get something like Jupiter, right? The critical core mass is, depends on a lot of things, but you should be thinking sort of few Earth mass, critical core mass. You build up an embryo that big, then if you get sort of 10 Earth masses, you can grab a few hundred Earth masses worth of gas very quickly, right? So this is the typical scenario for how we think of how Jupiter formed. The problem is this planetesimal accretion is a bottleneck, right? It can take 10 million years. And that's a problem if the gas disappears in 10 million years. So this is a long-standing issue with core accretion models. Is it efficient enough to be able to do that? We actually think now with some development that it can be efficient enough, and you can do this in maybe a few million years. But there's a really interesting alternative that's been proposed called pebble accretion rather than planetesimal accretion. And that is, maybe you don't need to seed everywhere in the disk with lots of planetesimals, as long as you have some, and you have a larger population of smaller solids, little tiny pebbles, grains of sand, rocks. It's possible to actually accrete enough mass in those pebbles onto the planetesimal seeds to grow very quickly, right? The key is being in a gas-rich environment, which if you can precipitate the formation of planetesimals fast enough, you could potentially actually do pebble accretion, and then you don't have as much of a timescale problem. Right? So this is the sort of core accretion model of planet formation. So there are a number of challenges with this model, but one of the things that we sort of come back to is the initial conditions, right? Where do we get the planetesimals in the first place, right? That's sort of the big issue. I'm going to talk a lot about these two initial conditions. One, having a smooth gas disk, and two, that it's seeded with planetesimals, that you, at the formation of the disk, that you have 100-kilometer bodies everywhere. That's not actually the case. In the molecular cloud, the disk itself is inheriting solid particles that are sort of micron-sized particles, like cigarette smoke, right? Those particles, to get to planetesimals, right, have to grow, tens of orders of magnitude by coagulation in 1 million years or something, or less, to make planetesimals, right? If they just accrete in a binary sense, one particle encounters another one. So the small dust particles are the challenge. How do you get from there to planetesimals, right? So we can actually do simulations of this growth process at the early stages, and you can do laboratory experiments as well, right? You can, in a microgravity environment, in the space shuttle, in the Vomit Comet spacecraft, and drop towers, where you just drop the whole experiment with a high-speed camera and watch the coagulation of particles in a vacuum, right? You can actually see and model that you can grow from micron-sized particles to pebbles, millimeter, centimeter-sized particles, pretty efficiently, right? We're talking, less than 0.1% of the lifetime of the disk, right? So that's actually easy. It's fast. The problem is that, it's quite difficult to do experiments when you actually are throwing rocks at each other in gravity. I don't know about your personal experience, but one thing I've never seen happen is two people throw rocks at each other and they stick together. That won't actually happen very much. And the reason is basically part of the physical reason that we run into a problem here. At about centimeter sizes, give or take an order of magnitude, you hit a couple real roadblocks. One of them is that the collision energies of those particles tend to be destructive rather than constructive, right? So you actually have, instead of the growth to a larger size, when you have a collision, you'll actually have fragmentation, right? So you're going in the wrong direction. That's not good. But there's actually a bigger problem than that. And it's related to what happens to the particles when they get to that size when they're embedded in the gas disk. And that is that they start to decouple aerodynamically from the flow of the gas disk, right? And this is sort of the quintessential problem in planet formation that, people have for 50 years liked to gloss over. And there have been a lot of explorations of how you might get around it, but observationally, we haven't had much access to them, right? So what happens dynamically in a smooth gas disk like we've assumed, right? If this is your pressure profile here, a little parcel of gas anywhere in that disk will feel the centrifugal force around the central star, but it'll also feel a pressure gradient force directed in the opposite direction, right? And then you can basically calculate the motion of that fluid is not quite the same as the Keplerian motion because we have a small negative pressure gradient in a smooth disk, right? And what happens is you end up getting a velocity deviation from the Keplerian flow. So this plot here is the velocity deviation and negative velocity deviations are slower motion. I'm depicting as blue. If there were faster motion, there'd be red, but you can't see any of it. So what happens is the gas is actually not moving like Kepler's laws. It's moving slightly slower. Slightly meaning like 1% slower or less. So you wouldn't think that actually would matter, but to the objects, the solid objects embedded in it that want to orbit at Keplerian speeds, they feel that velocity difference like a headwind, right? Like a drag force on them as they aerodynamically decouple. If you're really small particles, you're fully coupled to the gas and you just move slower than Keplerian with the gas. If you're a huge particle, you don't care what the gas is doing. But in this sort of in-between regime, which happens to be pebbles in most of the disk volume, what happens is that those pebbles will actually migrate quite a bit. So this plot is the velocity of particles of different sizes. Micron-sized particles are doing what the gas is doing. These are the radial velocities. And the pebbles are moving inwards, negative velocities, very quickly. This is a unit that, even to astronomers, is comical. But it's astronomical units per 1,000 years. But just to sort of translate that for you, at 100 astronomical units, the orbital period is 1,000 years. So basically, you're losing 10% of an orbital, 10% of your distance to the star in one orbital period. It's very fast migration, right? We call this radial drift of the pebbles, and it basically leads to a distinct segregation spatially in the locations of the solids. Basically, all the pebbles drift inwards very quickly, closer to the star. This is where the idea of the pebble accretion comes from, is that you know that if you can form planetesimals in the inner part of the disk, you have this flow of pebbles that they can grab and eat and grow. The problem is that basically this creates a barrier to further growth. When you get to about a centimeter size particle, it will move away before it collides with another particle to grow. So you're stuck at that size, right? And this is a big problem if you ever want to make planetesimals in the outer part of the disk. But what if I just change the pressure profile a little bit? So this is just a simulation where we just multiplied that same pressure profile by a sine wave. This is a mathematical toy, right? But you get enormous velocity deviations in these little concentrations located at the local maxima in the pressure, right? And the particles will then migrate towards those local pressure maxima in what we call traps, particle traps, right? So they actually accrete into these traps. The amount of the pebbles relative to the gas approaches unity, and when it gets to about 10%, you have the opportunity to drive various hydrodynamical instabilities that can basically sort of lead you to a runaway effect where you further concentrate the solids. This is the one sort of surefire way we know to make planetesimals almost instantaneously, is by getting high concentrations of pebbles at specific localized positions in the disk, right? So this is really what we want. And all I did in this model is perturbed that gas density profile with a 10% amplitude sine wave, right? Obviously, you can't just randomly do that in disks, but I'll explain why we think those things might exist. So the basic underlying idea is that there's an enormous range of fluid instabilities, hydrodynamic or magnetohydrodynamic fluid instabilities, turbulence, various aspects of the gas flows in disks that should drive pressure modulations, and they could be much more than 10%, right? And they need not be perfect little sine wave rings either, right? They can be fairly complicated structures, spirals, any of these things. But the key point is that natural fluid processes in the disk will drive localized pressure maxima that can then concentrate the solids, the drifting solids, into those locations. That's where you assemble planetesimals. You continue to accrete the drifting pebbles, and that promotes fast core growth, and then you get planets. This is the sort of saving idea of the core accretion model and how you can actually maybe make planets quickly. But we actually, that's just a hypothesis, right? We actually want to find these substructures. Substructures meaning small-scale pressure substructures in these disks. This is extremely hard, right? The fluid dynamical models that actually create these pressure substructures are small. We think they're typically the pressure scale height of the disk, which is about 10%, 5 or 10% of the radius at which you're talking about. So if it's a 10 astronomical units radius, like where Saturn is roughly, you'd have to have a resolution of 1 astronomical unit to hope to resolve any of these things. This is just giving you some numbers. The sort of benchmark number that we're thinking of is, you know, in the outer part of the disk, we're looking for 30 milliarc seconds, right? So your eyes have a resolution of about 30 arc seconds, right? So we're going considerably better. 30 milliarc seconds is roughly me being able to make out the size of my toddler in Boston if I had a straight shot, right? It's a pretty substantial angular resolution to get to. You need some good sensitivity, but as I've shown you, you don't need huge pressure perturbations to do this. The key is to look for the trapped solids, to look for the millimeter, centimeter size pebbles as your tracer, right? So that millimeter, centimeter size particles tells us that we want to look at millimeter, centimeter size wavelengths, because dust particles emit a thermal continuum, just heat re-radiated from the energy they absorb from the star's radiation at a wavelength comparable to their size, right? So we're looking at millimeter, centimeter wavelengths. On the left side is the thermal continuum emission. This is just basically the glow of pebbles in a disk. And you can see, maybe it's a little difficult, but you can see that basically there's a central core, nothing, and then there's a little ring in this example. And we get this from just imaging directly with interferometers. And then you've probably been watching this movie. I guess it stopped. Let me get back to it. You've been watching this movie. At the same time with an interferometer, you actually get a measurement of a molecular spectral line, or various molecular spectral lines, depending on what they are. This is carbon monoxide in the same disk, the same scale, same resolution. And what you're actually seeing is me stepping through different projected velocities where that emission is actually happening. So you see this distinctive rotation type pattern. That's actually the gas disk rotating. So the nice thing about this is you get, from the molecular lines, you get the intensity of the emission, which you can probe things just like you can in the continuum. But you also get the spectroscopic information, so you're actually learning about the velocity field directly. As long as you have a mission, you can backtrack out what the velocity field is. All it's related to is the geometry of the disk itself. So this is what I've been working on most of my career, actually. And the reason was that when I was a graduate student at University of Hawaii, the Smithsonian commissioned the first sort of millimeter or submillimeter astronomer called the submillimeter observatory interferometer called the submillimeter array. Right? It's a partnership between the Smithsonian and the Academia Sinica in Taiwan. And this is a picture of it on the summit of Mauna Kea, and after a big storm. But it's 8 6-meter dishes. It operates between 180 and 420 gigahertz. And it has baselines going out to about half a kilometer. Right? So that can give you an angular resolution of about 0.3 arc seconds, which is about 1,000 times better than your vision. And really, it's been a big driver of cutting-edge instrument development, which is now being deployed in other interferometers as well. But we invested a lot of effort here laying the groundwork to sort of understand the evolution of these disks, looking at their demographics, how they change with time, chemical inventories. And I'll say, like in this plot in the, I don't even see my little thing anymore, but the plot on the lower right, you got the first hints of substructure where we see this sort of blurry ring in these protoplanetary disks. But really, to do this, I think this might have died. Maybe I can just... I think the battery ran out in this.
You have to say next slide.
Okay. Can you go to the next slide, please? Thank you. Oh, one back. Oh, dear. Well, can you go back a few? This one. Thank you. Right. So the big advance in the field was getting more angular resolution. And to really do this, you need more angular resolution and sensitivity. And so in 2012, an international partnership of 23 countries commissioned this telescope called ALMA, the Atacama Large Millimeter Submillimeter Array, in the high Atacama Desert in Chile, altitude 16,000 feet. So this is a huge ground-based facility, right? Different countries wanted to build their own things, and we partnered together to build a facility that costs of order $1.5 billion. U.S. share is about 37%. It's comprised, it's got 54 12-meter dishes, and 10 7-meter dishes, right? And they all act in concert to synthesize emission from just like the submillimeter array, but with approximately 100 times the sensitivity and substantially better angular resolution, right? So the longest baselines of this interferometer were commissioned in 2014, and they're 16 kilometers across. So basically, you're synthesizing a telescope with the angular resolution of a telescope that would be as big as the district. Right, 16 kilometers, thereabouts. Maybe that's not true. I think it's roughly that. So this gives us sort of 10 times the resolution that we had before. These are some pictures of ALMA. Can you go to the next slide, please? Thank you. So the opportunity with these baselines is sort of, just to give you an idea, this is not sort of me trashing my own previous work, but this is what we were working with in sort of 2012. These were resolved images of nearby disks, and we get sort of 10 independent resolution elements, and you could trace out roughly where the mass and the solids are. And if you could advance to the next slide. This is what we see with ALMA when we image them at 30 milliarcsecond resolution. Those sort of indistinct blurs, which drove the understanding and the perpetuation of the smooth model for core accretion, end up not being so valid. What you see is small perturbations in the disk. In these cases, usually very symmetric rings and gaps in the emission. Next slide, please. Here's just a gallery of a handful of my favorite images that we've taken so far with ALMA. And there's a little scale at the bottom left that basically shows the orbits of the giant planets in our solar system, Jupiter, Saturn, Uranus, Neptune, just to give you an idea of scale. These disks can be substantially larger, but you also see perturbations on the scales of our planetary system. So if you look at these images, you actually see that they have similarities, but they're all quite diverse, in fact, in their morphologies. Next slide, please. The key point that we've learned is that these substructures are common. And by common, I mean we have not found an example of a disk where you do not see these substructures if you have an angular resolution that allows you to see that fundamental scale that we think they form in the fluids, the pressure scale height. Basically, they're ubiquitous. We always see something. What's interesting is that they don't really seem to have the perturbations, the local pressure maxima don't really seem to have preferential locations, and they don't really care what kind of star you're orbiting either. Next slide, please. So the most common morphologies, as I said, are these rings and gaps. And the features, when we measure them, are quite small. In fact, in the continuum, they're usually considerably smaller. They're not resolved, right? We just sort of barely see them. They're still quite blurry. They can be smaller in the pressure scale height, which is fine in the continuum because they're concentrated dust particles at the center of these pressure traps. They're quite sharp when we actually resolve them. They're quite sharp features. And that means that there's not a lot of diffusion away from the core of the pressure trap, which means that the turbulence is fairly low, which is really good for planet formation. You don't want a lot of disturbances to actually the aggregation of these particles. And in these rings of emission, we'd estimate that you'd have several tens of Earth masses of material in those rings, right? So that's really great if you actually want to accumulate mass into cores that can become giant planets in the future. The contrast is basically the amplitudes of those pressure traps are sort of all over the place, a few percent to maybe more than a factor of 100 as well. Next slide, please. Okay, so if we look at the gas in these cases, right, on much larger scales, we still see rings and gaps. It's a little more difficult to see. Again, these are carbon monoxide images where I've integrated across the spectral line. And you know, you see concurrences between the continuum locations of the features and in the line in some cases, but often you see features in the lines where the continuum is no longer there. It's because the pebbles have migrated in. And you actually see direct signs of pressure maxima in the kinematic perturbations, right? You see actually the sort of peaks in the gas pressure and the velocity profile that you expect from pressure peaks. That's what the plots on the right are showing. Next slide, please. So we do see that asymmetries, right? Most of those figures that I showed you had point symmetry in the sense that you know, primarily they look circularly symmetric, just projected at some angle to our line of sight. Strong non-axisymmetric features are less common, but we do see them. Here are 3 examples where you see these little arc features located outside or inside of some ring or gap, right? And those, basically, in this field, the one thing that we all seem to agree on, those are actually very similar to the predictions that we'd expect from a hydrodynamic vortex, right? Where basically some fluid instability, Rossby wave instability, some other fluid instability, will actually create a circulation in the gas flow, and that traps particles in that gas flow and concentrates them more and more. So that's what we think we're seeing in these cases. Next slide, please. I guess I'll skip over this, but basically, if we remove smooth symmetric models in some cases, we start to see lower level asymmetries, and we're really just starting to discover those. I'll leave that for later. Next slide, please. So the thing that, in my mind, is the most stunning to come out of this are these large-scale spiral patterns, right? Where these disks look like spiral galaxies. just at a much different physical scale and tracer. They're not stars we're seeing anymore. It's the pebbles trapped in these spiral features. What's interesting, if you look, I'd say at the left one at about 120 AU, where I've done a sort of polar deprojection where circularly symmetric things are vertical in these plots, right? And the spiral arms are these diagonals cutting across it. But at 120 AU, there's a vertical feature, a depletion of emission. And that means there's a circular gap at that location. So you see that actually it's not just a simple one hydrodynamical feature. It's mixed modes of fluid instabilities interacting together in this example. Very impressive. I haven't seen anyone actually able to explain that yet. Next slide, please. Right, so these mixed modes are actually becoming more and more prominent. And I show a couple cases on the left here where you get an actual size difference between the continuum emission, very small in the center, of these enormous gas disks, which you see in blue. And the gas disks have these spiral protuberances and so on and so forth. And the pebble disks at smaller scales are perfectly symmetric rings and gaps. Right? So many different physical processes are operating here, and it really depends on how you look at the disks to be able to discern what's happening. Right? So on the right, I'm actually showing the same disk to the same scale. On the left, you're seeing a millimeter continuum image where the pebbles are located. And on the right, you're seeing reflected light off the surface of the disk at basically 1 micron. Right? And you see very different looking appearances. And the reason is that basically, again, on the left, you're tracing pebbles. And on the right, you're using dust, but it's an indirect tracer of the gas. Right? So it's the same type of scenario as the left-hand side, because the right-hand side is very small dust particles, micron-sized dust particles that are just doing what the gas is doing. So the key point is that basically the gas reservoir and the drifting solids can evolve to very different configurations. And again, that's sort of the violation of the underlying principle of the core accretion model, but the thing that actually precipitates us to be able to form planets efficiently in that model when we relax those assumptions. Next slide, please. So here are a few lessons learned from this observational study work. The very high prevalence of disk substructures implies that there's some universal process or processes that are driving these features. And generally, the characteristics, sizes, morphology, symmetry, so on, of the locations and scalings of these substructures are broadly consistent with expectations from magnetohydrodynamic instabilities and numerical simulations of the disk fluid, right? And we think that in these substructures, they're very promising venues for building cores and more efficient planet formation. However, if you'll go to the next slide, or next feature, those things could actually also be formed very easily by interactions between the disk material and newly formed planets that we have not yet seen, right? These interactions are basically what drive the evolution of the planetary system once the planet has formed. Basically, the disk and the planet pushing back on one another and their hydrodynamic interaction is what can make the planet migrate into the inner part of the disk like we see in the planet population today. Next slide. So the reason that this idea has become more and more attractive, at least in my mind, is a few things, and I'll show you each of them in turn. One is that basically it's pretty easy to actually simulate with planet disk interactions, hydrodynamic simulations. It's pretty easy to make simulations that look a lot like the data, right? This is a little bit unfair because we have a lot more development of these kinds of models to be able to explore. But in the top left, you see a measurement, and the bottom and the one next to it, you see a model. And you see all these rings in this system and all these gaps in this system. And you might think, all right, well, to make this model, we've put in 4, 5, or 6 planets, and they carve out these gaps. But in reality, we've put in one planet in that biggest of gaps that's about the mass of Saturn at about 100 astronomical units. And that planet can actually then create all these substructures by the spiral wakes it drives in the disk at all these different locations, right? So in a sense, it's a little more elegant than invoking many hydrodynamical instabilities when you can just sort of put in one planet It's a little bit of a cheat because there's other parameters, and we tuned it in this model. On the right-hand side, you see what I would call velocity deviations, right? Which is basically where we've removed a model of the Keplerian motion of the gas disk. So all the residuals that you see there, small-scale residuals, are related to disk-planet interactions. In the bottom right of the model, the planet is sort of at 9 p.m. or 9 o'clock on the clockwise, and it's a gas giant planet that drives these spiral waves that basically create these velocity substructures. And in the data, we see very similar looking tight spirals that are basically the prediction of planet-disk interactions. Next slide, please. So there's these simulations that basically agree, but then there's sort of what I would say is a little bit more of a smoking gun of an indirect sign of planet-disk interactions. And that is that these sort of spiral wakes have a distinctive velocity signature, right? So the top two plots are showing density on the left and velocity on the right of a model where you've plunked a planet down, a 3 Jupiter mass planet down at some distance from the star. So you can see the planet drives these spiral wakes in the density structure of the gas, but it creates this very distinctive flip in the velocity motion right around it. It goes from sort of moving faster than the planet and slower than the planet, Keplerian motion. And if you look at specific velocities of the spectral line emission, in this case carbon monoxide, on the left you can see what the simulation predicts. And if you look, this is where I really wish I had a pointer, but if you look in this sort of upper left quadrant, you see this little kink, this little like lightning-shaped pattern, right? And that's a distinctive signature. And this is a real observation of that of a system where you see that distinct signature. Because these are azimuthally and radially localized, we don't think that they can really be coming from a fluid instability scenario. It requires an actual massive perturber, massive in the scale of the fluid, which is a planetary perturber. This is just another example. You can see this little wiggle in the emission distribution as well. Right, so we think that these are actually planetary wakes, and we're going to try and actually image the planets with the James Webb Space Telescope when it launches. Next slide, please. Okay, and so this is the sort of example that brings everyone over the edge. It's one bona fide example where you see a connection between planets and the disk structure itself. So it might be a little difficult to see what's going on here, but this is a disk observed in scattered light. The star is massed in the center, and you see one point source that looks like it could be a planet, and it is. Next slide. But there's another one, too, and it's sort of hidden in the scattered light for the disk. This is an image in the H-alpha line, the hydrogen recombination line in the optical, where you see intense spectral line emission from accretion onto these planets from the disk material, right? Next slide, please. Next slide. This is our ALMA image of that system. Amazingly, we don't see that bright planet, but the fainter one that's bright in the accretion pops right out. So that's not emission from the planet. What you're seeing there is actually dust trapped at the planet. It's actually material orbiting the planet that will settle into a satellite system like the Galilean moons of Jupiter. Right, so we call it a circumplanetary disk. Next slide, please. You can zoom in here. It's just a closer view of it from this. So the amazing thing about this is that these planets are sort of 4 or 7 Jupiter masses. They're at 30 astronomical units or thereabout from their star. And they've carved out this giant cavity around that's encircled by this ring in the disk. And that's basically just a true planet-disk interaction, the kind of thing that we're looking for. We hope to find a lot more of these in the coming years. Next slide, please. So I wanted to just go back to this plot and give you an idea of what we could learn if these actually turn out to be planet-disk interactions and not the precursors to planet formation, but the immediate consequences of planet-disk interactions. We can actually measure the properties of these substructures and infer what the masses and locations of the planets that would be required to create them if that was the origin story. Next slide, please. And they're all in this unpopulated area that we haven't quite got to with exoplanets yet. And that's very exciting. It could tell you that planet formation is much more universal and different than we thought before. Obviously, these are prime targets now for direct imaging as the telescopes get more sensitive to those things. Next slide, please. So I did want to sort of wrap up and sort of give you an idea of where we're going in the future. And that is basically following in line with this. There is intense interest now to use the properties of disk substructures as guidance to look for giant planets at their formation epoch and trying to find them interacting with their disk material. So you do this, basically only way to do this right now is with direct imaging, right? You do not have the ability with eclipses, transits, because those planets all have to be very close to their star. Radial velocities, again, you have to wait a long time to actually see the orbital period. But if you can get direct imaging measurements that are much more sensitive, which we will in the coming decade, with facilities like the James Webb Space Telescope, which will be really outstandingly sensitive for direct imaging if you're far enough away from the central star, because it has a fairly large coronagraph for these young stars. So there's a handful of programs in the first suite of observations of JWST when it launches next week, we all hope, and then eventually makes its way out and starts taking observations. We'll see if those planet-disk interactions are indeed prominent in those systems. And what we're also looking forward to is a new generation of ground-based telescopes that sort of make a big leap from the sort of 8 to 10 meter class telescopes that we have today to sort of more in the sort of 25 to 40 meter range, right? And 3 of these telescopes are in under construction in some phase or another. 2 of them in the US, the one that I'm more familiar with is the Giant Magellan Telescope, because the Smithsonian and Harvard are partners in that facility, which is a sort of 26 meter telescope made up of 7 individual mirrors that eventually will basically have a very deep and sensitive imager where we think we'll be able to get down to sort of Saturn mass type planets that you can detect in the infrared. Right, so it'll go a long way towards these things. So JWST will actually happen first, and then the GMT and TMT and ELT in the future. Next slide. So on the radio side, which is really where we're working on these disk substructures, there's quite a lot of plans for future development in the instrumentation, right? So the goal is to basically find and characterize the substructures that are smaller and closer to their host stars, more analogous to where we see planets in our solar system today. So ALMA, which is a facility I've been talking about, has been absolutely revolutionary. I mean, I hope I conveyed that to you in those blurry images that turn into these beautiful rings. But really, that is the feeling in the field. It went from something that was sort of notional to extremely impactful in a very short period of time as soon as they turned on that capability. So ALMA is actually in a stage of development now over the next decade where they're going to sort of commission some new receiver packages, particularly operating at lower frequencies that will enable us to look at slightly larger pebbles and see where they're trapped. And they're going to do some massive sort of sensitivity upgrades on the back end structure of the telescope. Basically, the goal is to get at least a factor of 2 in bandwidth. So, 40, 50% in raw sensitivity. And one of the things, this is why I'm showing this plot, this is a sort of Google view of the ALMA Science Conserve in the Atacama, which is basically, you can sort of see the roads in the center where it's located. Their goal is to actually expand to slightly longer baselines. They're hoping to get a factor of 2 in the baseline length, which is basically a factor of 2 in resolution. And, again, I don't have something to show you, but the central part of this is where the ALMA antennas are now. And they think they can move up to the north a little bit. You can't go too far past that road 27, because you see there the Chilean-Bolivian border. And you can't just build telescopes and run fibers across international borders easily. They do think they can go to the south, but what they'll do, you see this little road going to the east there. they're going to build, that sort of slightly goes downhill. They're going to populate antennas out there. So we'll get a factor of 2 in resolution, which is basically the difference between, seeing things at sort of 15 AU and seeing things inside of, closer down to 5 astronomical units, substructures at 5 astronomical units. And there's sort of an aspiration going in the future is building a sort of second generation of ALMA, where you're aiming for sort of 10 times the sensitivity, and that involves building a lot more antennas, right? So this is sort of an upgrade project that isn't the same cost as actually building the original ALMA, but it's actually building more antennas than the original ALMA with less stringent design qualifications. The timescale for that is to be determined. Next slide. What we're all really excited about, actually, is the next generation Very Large Array. So you've probably all seen pictures of Very Large Array in New Mexico if you've seen the movie Contact or many other movies. And the Very Large Array has been, doing fantastic science for 40 years, basically my life. And there's a plan now that's just basically been given the stamp of development approval by the National Academy's decadal survey for the next generation Very Large Array. So this is an entirely new facility that's planned for construction in the 2030s, and it will be 244 18-meter antennas, and then a smaller population of smaller antennas. And the amazing thing is the design of the interferometer itself gives you sort of really good sensitivity on baselines out to 1,000 kilometers, right? And so, again, almost 16 kilometers. The difference is that the NGVLA will operate at longer wavelengths, which are somewhat less sensitive intrinsically, although this will bring you up to the sensitivity you need. There's much less emission at those long wavelengths, but they're much more physically interesting for this particular science and many other particular science. So 1,000 kilometer baselines is big. The VLA right now is outside Socorro, New Mexico. It's basically an hour drive from Albuquerque. And the core of the NGVLA will still be there, but it will expand throughout the American Southwest, right, and neighboring states. And it will actually have a outpost for very long baseline interferometry for different kinds of science, all the way from Hawaii to Puerto Rico, right? So this is really a sort of generational new instrument that we're really excited to use. And I show some examples here. I guess the left ones aren't displaying as well as I'd like them to, but you can see the ones on the right, where you can observe something like a few Earth mass, the perturbations from few Earth mass planets at a few AU from their stars, right? So you really will be able to see like in situ Jupiter formation if they actually happen that way in these systems rather easily. So we're very much looking forward to that. The exciting thing for me is, this is the kind of thing that actually does happen in my career. And so we actually will get to use it as well. Okay, so next slide. I think it's the last slide. So I'd like to just sort of end again with just a statement, right, about where we're at. I don't want to recap every little thing, but the key is that these small substructures that we found in these disks around the young stars are really the essential aspects of planet formation. They are key for assembling planetary systems. It is possible that actually we're not seeing the things that are responsible for forming the planetary systems because that was a previous generation. What we're seeing is actually the planetary systems already formed and interacting with their birth environments, which I think is equally exciting as well. So thanks very much for your attention, and I'm happy to answer questions for you.
very informative lecture on a very interesting subject. We have time for the Q&A. Here's the procedure for questions. If you want to ask a question, raise your hand. Be persistent. Eventually, one of the runners will bring you one of the color-coded microphones. It will be on, and hopefully it will work. You do not need to do anything to turn it on. Just hold it a few inches from your mouth when you speak. I will call on questioners by the color of their microphone. And when I call the color of your microphone, please ask a question. Please refrain from making speeches. And when you ask your question, hand the microphone back to the runner so that they can bring it to another questioner. Please keep in mind, we do all this with the microphones because we want our online listeners to be able to hear your questions, and because this is all being videotaped and the majority of viewers of this lecture will be watching the recorded version, and we want them to be able to hear your question as well. So it's important to hold the microphone close to your mouth. YouTube viewers can text questions in the YouTube chat box, and they will be read aloud to the speaker for everyone to hear. So, do we have any questions? We have a question in the front row here. And the gray microphone is coming your way, Bob. And you could please stand up or just say your name and whether you're a member.
Bob Terry, I'm a member. I have a question about the circulation of these disks. Is it true, I think it might be true, the circulation of the star is the same sense as the circulation of the disk, is the same sense as the circulation of rotation of planets as they form. Is that generally true when you form planets? And what physics makes it more prevalent than having any other state when you get everything rotating and swinging around?
Yeah, that's a good question. And it's actually doesn't have an exact answer. But the idea in the simplest scenario, what you would have is that the star, certainly in the beginning, the star and the disk itself are rotating in the same sense. So the challenge, that breaks down pretty quickly, actually, we think. And the reason is that basically you have material that's accreted from the disk onto the star, and that's typically accreted along magnetic field lines of the star. So the magnetic field of the star is sort of like a dipole. So the material is lifted up and lands, at different locations in the star, and it can actually torque the motion of the star, and that has a back reaction on the actual disk itself. So the star's rotation axis can get torqued away from the disk's rotation axis, which you do see in some cases. The planets themselves, a similar kind of thing can happen. Of course, in our planetary system, the planets don't orbit in the same sense as they rotate around the star, and we primarily think that that's related to actual impacts at the late stages, right? So Uranus, for example, is sort of 90 degrees. The Earth is 23 degrees, or else we would have different weather. But indeed, the simplest scenario where you discount those physical processes where you either are torquing the body by the sort of environment of the disk, or hitting it with big things, you would have that sort of preserved rotation. Yeah.
So I have a question that maybe is, then we'll go to, is that Erica or Bruce? Bruce. I noticed you put in a sort of pre-planned perturbations. You showed that sine wave. Did you look at noise? Just injecting a certain amount of noise into the system?
Oh, yeah. No, that's a great question. In fact, yes, that was how the early actual studies of this were done, was I wouldn't call it noise, but you'd put in turbulence, right? You'd inject turbulence on some scale, and you have like a Kolmogorov spectrum of turbulence that's generated. If you can perpetuate that turbulence, indeed, you would get disordered substructures, right? You'd get little transient collections of dust particles that could do that. So the interesting thing is, in disks, partly related to the orbital shear, and partly related to the nature of that turbulence or at least what we think is the turbulence. Turbulence can actually go from disordered to ordered pretty quickly. It can basically create large-scale vortices and large-scale rings, spirals, and so on that you see in the simulation. So you might start with just churning up the disk, but you still have this churn, but you'd also have these ordered structures like what we see. But there can indeed, and we would expect there to be a spectrum of substructures at smaller and smaller scales that are less ordered, clumpy, that we'd see, but we don't have the resolution to see that yet. Yeah, that's a great question.
Gray?
And I am a member. How many of these disks have been imaged at high resolution, and how many of them show this types of ring structure? Have we seen any that are just smooth?
Right, so I lost count of the exact number, but I think it's something, of order 30, 40 disks that we've observed so far, which is quite a small fraction of the nearby disk population where you could do this, right? So, I guess I didn't emphasize it quite a lot, but this isn't easy to do and requires a lot of competitive observing time. So ALMA, when you propose to use ALMA, basically there's a 7-to-1 oversubscription rate, right? So it's a little like winning a mini lottery every time you get things. But indeed, so they commissioned it in 2014, the first time you could observe in 2015, but they haven't had the long baseline configurations now because of COVID for a while. They're just going to go back to them next year. So it's a reasonable number for where we're at. The answer, how many could you do? Hundreds, right? And if the cosmologists and extragalactic scientists would seed the telescope, we would do hundreds. Now, are there cases where the disk still looks smooth? And that's a little complicated, but the disks that are very small, right? So the disks where the pebble distribution only goes out to, say, 10 or 20 AU, many of those appear smooth. But we don't actually have the resolution to see the right scales, to see the substructures when the disks are that small. So all you would see in those cases are the big substructure, the biggest substructure, like the tip of the iceberg. In some cases you do see those, but often they do appear smooth, but that doesn't really mean they're smooth, right, in that case. Otherwise, the cases where you resolve the right scales, you always see something. Yeah.
We have a question from the web. Laurel? You read it out loud?
Lise asks, can you tell us more about the PDS-72 detected planet system? Is the primary an AFGK or M star? Is there room for another planet in the system? How big is the outer disk versus our Kuiper belt? Additionally, they ask, planetary nebulae is a very archaic term that was applied because older astronomers thought the extension of the system meant it was like an extended solar system. But I think the first one was the actual question.
Okay. Hi, Carrie. All right. I'm going to have to ask you to repeat that question because it was very long. So the first thing was about, I'll start with what I remember, the PDS-70 system, the system where we have the directly imaged planets where we see one of them with ALMA. So PDS-70, the star itself, I believe, is an F star. It's sort of, 7-8 million years old, something like that. I don't remember beyond that what the question was.
Yeah, I'll just repeat the actual question.
Yeah.
Can you tell us more about the PDS-72 detected planet system? Is the primary an AFGK or M star? And is there room for another planet in the system? How big is the outer disk versus our Kuiper belt?
Right, okay, so I said it was an F star. Is there room for another planet in the system? That's an interesting question, right? So I think we don't. So what does he mean by room for another planet in the system, right? It's basically, you can stick planets wherever you don't see disk material, but you can't quite do that because there's there's sort of a dynamical stability argument. If you put too many planets close together, you wouldn't see the planets that we see necessarily on the orbits that we see them. The problem is that we don't really know the orbits of those planets very well yet, because they were only detected a few years ago. We haven't actually traced out their orbital motion very clearly yet. My understanding is that there's some argument that there could be a planet much closer to the star, near the inner edge, or the outer edge of that inner fluff of disk emission, but we don't actually know. I think the outer planet is at a location of 32 AU or something like that, and then that ring of material, which could be an analog, an early analog of the Kuiper belt, would be at something like 40, 50 astronomical units. Very similar to what we see in our solar system, if I recall the numbers correctly. Yeah.
We have another question up here. Gray microphone again.
Hello, Charlie Huttner. I am a member. So you're talking about planetary structures, flat disks, and that makes me think about galaxies that are also flat disks. Is there any part of the research you're doing now that might relate to how galaxies are formed and then how galaxies might circulate around something that's even bigger?
Yeah, that's a great question, especially when you see those spiral patterns, you immediately think galaxies. So there are some parallels that could be, that invokes the same fluid dynamical issues, but there are some pretty important differences. Like, one is that the dynamics in a protoplanetary disk are to zeroth order dominated by the central star, which is most of the mass of the system. In a galaxy, that's not true. You have a much more distributed mass distribution, and self-gravity is really important, right? The spiral that you're looking at in a galaxy, the neighboring parts of the disk actually have a substantial pull on it, which is not really true in protoplanetary disks. So there's some analogies, but they're not really sort of one-to-one dynamical scenarios. Of course, the different situation is too is we're looking at an actual fluid, and in a galaxy you have a dark matter halo that complicates things, and you have actual stars, not just gas in the system as well. So there are particularly looking at these sort of spiral arms as sort of like eccentric resonances, right? That you see in spiral galaxies. People have been investigating that, but there's a lot of differences in the detailed physical arrangements of the systems that make it complicated. It's a similar question I sometimes get asked about Saturn. Right? You look at something like Saturn and you see this ring system where you see these gaps in these rings. You see these little moons that shepherd the rings, right? And that's basically you think that's just sort of a scaled down analogy of a planetary system perturbing the gas disk. And it's similar, again, in many ways, but you have a very different scales in the system that actually make some interesting dynamics happen in the Saturn rings that probably won't happen in protoplanetary disks. Yeah.
If I understood one of your slides, I think you were showing a disk around a planet.
Yeah.
And so is that similar to the formation of planets around a star? Those analogous processes, or are they really different?
That's an interesting question.
Solar system. And let me go and add one more. Did you actually see evidence of a moon?
No.
Around an exoplanet?
No. There are people.
But you're hoping.
Yes, and there are people looking, especially in the transit systems, the eclipsing systems, that you would see it in the light curve, a small perturbation. This is material that will, presumably eventually form a satellite system, like the Galilean moons, which also orbit in a plane around Jupiter, because they formed in a circumplanetary disk. The process of actually building up satellite systems is much less developed, but basically it's quite analogous. The same ideas apply, right? You just don't have as much mass, and you don't need as much mass to be able to do it, and you probably don't have a ton of gas, right? Those satellite systems don't tend to have rich atmospheres. So it's a little easier in that way. You only need to accrete the bodies themselves.
Now, in our solar system, people don't think the moon formed that way, our moon, but they think some of the other moons have formed that way?
Yeah, certainly. So the 4 Galilean moons of Jupiter are the case that people think of, because they orbit in a plane, confined to a plane around Jupiter. So they must have formed in a setup like that. And the difference is basically that your time scales for forming those and the mass available to form those. Yeah, you don't think that the Earth and Moon formed together. The Moon came later.
That's what they say.
Yeah.
Well, what about the Saturnian moons, of which there are, what, 60-something, 70?
Yeah, I mean, the Saturnian system is a little more, I guess I'm a little less familiar with the detailed orbits of them. It's a little more complicated because you have the biggest moon is actually quite far out. Titan is quite far out away from the system, but yeah.
We have a question here from Al Ehrlich. Al?
Like I am a member of the society. I think I know that the answer to this is no, because your modeling fits your observations so well, but is the mathematics that underlies the work you do anything like the nonlinear dynamics that leads to so-called chaos, wherein very small changes in or differences really in the initial conditions can produce profound changes in the outcome?
Yeah. Yeah, so that's an interesting question. I do not have a clear answer to that. I do know that in the dynamical interactions, even at late stages, where you have multi-planet systems and maybe you have a reservoir of bodies like a massive Kuiper belt, there are people investigating that basically if chaos can drive the long-term evolution of the system. I don't think that's been examined when you have a gas-rich environment, in the sense that basically the gas dominates the interactions between the bodies and damps out a lot of dynamical behavior. Once the gas is gone, all bets are off, really. And there are a lot of simulations that basically show sort of chaotic interactions and even the wholesale ejection of an enormous amount of mass from systems once they basically, migrate into some configuration that might drive a lot of material away. But yeah. Yeah.
We have another question from the web. Could you read it slowly for me?
Thomas Artman, former member, says he will renew, asks, do people look for planets in planetary nebulae? He knows that the term does not mean that there are planets in them. However, given the amount of gases and dust and whatnot in a planetary nebula and emanating from the star, would traces of planets be visible? Globs of dust? Anything?
Yes, that's interesting. I am, that's not my expertise, so I might be missing something. I'm not particularly aware of things. However, I think, a really interesting angle on planet formation is being learned by looking at the remnants of solar-type stars, white dwarfs. And occasionally in these white dwarf systems, actually not occasionally, it's quite often in these white dwarf systems, you can either detect excess emission from dust, so there's some debris in that system. It did not survive the planetary nebula asymptotic giant branch phase of the late stellar evolution. It's new debris caused by material being, asteroids basically, or planetary type bodies being ripped apart as they get to basically the Roche radius of the system. Sometimes you even see gas from these, outgassing from these particles being ripped apart. So, and looking at these white dwarf systems, which is sort of after the planetary nebula phase, you can actually learn about the sort of material composition of the planetary bodies in that system, long after the star has, died. It's a really fascinating subject.
What kind of computational resources do you need for these simulations?
So, it depends on the actual simulation you're talking about. You can do pretty good planet disk interaction hydra simulations on a laptop.
A good laptop.
Yeah, a good laptop and a little patience or whatever, and a lot of expertise. The magnetohydrodynamic simulations, where you're treating the non-ideal terms, where basically you have low ionization in these disks, and you have to treat all the complications of it, and you try and model it in 3 dimensions, then you're using basically the world's most powerful supercomputers and millions of CPU hours, right? So I mean, it really runs the gamut of the full range of computational resources in the field, and it just depends on the kind of problem you're tackling. The most important stuff are these global MHD simulations that people are doing, but they're by far the most challenging and still resource limited in some sense.
I'm going to have to go play with my computer after this. I need to mention the next generation very large array would have a point in Puerto Rico.
Yeah.
Is that going to be at the site of Arecibo, and is that part of the plan to try and get funding to build something to succeed the collapsed dish?
Well, yeah, I won't. I'm not party to the political machinations of these things, but the idea is that basically you have observatory infrastructure and engineering and scientific expertise at Arecibo. That's really kind of unparalleled in radio astronomy. And the idea is basically you need to populate on sort of Earth-sized baselines to do the very long baseline array, this upgraded version of things. So it's sort of a natural place to site outposts for the VLBI measurements. And that's the intention of the National Radio Astronomy Observatory, is to do that. I don't think that replaces the other ideas for the development of Arecibo, but it's certainly a part of it.
Yeah, it's an addition.
Yeah,
another support. Yeah. I should mention, in addition to the Arecibo talk, we've had a talk on ALMA when it was first built, and we've had talks on the GMT and the TMT, and we're going to have a talk on the European Extremely Large Telescope in the spring. And we're going to have our second talk on adaptive optics at our next meeting. So we are trying to cover this territory here.
Sounds like you're doing a great job, yeah.
So again, if there are no more questions, hearing none, let me thank you very much for coming here and giving this talk.
Thank you.
Before you go, I have a signed copy of Volume 1 of the Bulletin of the Philosophical Society of Washington, in which you can learn why it was founded,
That's great.
who founded it, why they named it philosophical instead of something we currently would understand as science. And you can read some early reports on the meetings, including a discussion of expeditions to view the transit of Mercury to measure the size of the solar system, and the new monetary system in Japan, which seemed to have been of great interest because there are numerous talks on it, and a method to calculate pi to 30 decimal places that was pointed out to be by a physicist, Nima Arkani Hamad, who thought that was pretty interesting. Well, he did mention that he had calculated pi to 30 million decimal places. Anyway, thank you so much.
Thank you.
A real
Thank
pleasure.
you all.
Before you go, we have a few closing announcements. And I think I need the next slide here. The 2452nd meeting will be on January 14th in the new year, 2022. The speaker will be Olivier Goyon, astronomer at the Stewart Observatory, professor at the University of Arizona. He will be giving a fairly technical lecture on the scientific principles and technology and engineering details of the adaptive optics deployed on large telescopes. His lecture will provide additional depth to his first lecture on the subject not very long ago. The meeting and the lecture will be via Zoom because he's going to be busy in Hawaii, probably on Mauna Kea, or at least in Hilo at the foot of Mauna Kea. By the way, did you know that Mauna Kea, measured from the bed of the ocean, is the tallest mountain on Earth? Yes. Excellent. I love this group. The president's lecture that was originally scheduled for this date will be given at a later date when we can meet in person. The 2453rd meeting will be on January 28th, 2022. The speaker will be Ray Lugo, CEO and principal investigator of the Center for the Advancement of Science and Space, the organization tasked with managing the U.S. National Space Laboratory in Space that we know fondly as the International Space Station. Ray will be discussing the International Space Station and its future. Please join us for these meetings. Finally, next slide, let's thank tonight's volunteers. Robin. And with that, I will now adjourn the 2451st meeting of the Society. I wish everyone a good morning, afternoon, evening, or night, as the case may be where you happen to be. The meeting is adjourned.